afternoon. This is CIVE 638, Sedimentation Engineering, and this is class 14.2, meaning 14th week. I'm sorry, this is class 14.1, the 14th week, the first lecture. We do not have a second lecture this week because of the Thanksgiving holiday. I'm Professor Victor Ponce from the Department of Civil Engineering, San Diego State University. And the subject today is our second lecture on scour. Next Tuesday, we're gonna do a third lecture. So I intend to cover this subject in 2 more lectures. Scour, very important subject, by the way. Most bridges that fail due to scour. We know that for a fact. So let me go in here and share the screen, and I'm going to ask if you guys are actually seeing the screen, the syllabus, this part 2 syllabus.
Yes, I see it.
Thank you. Thank you. And we were over here. We've been over here. We looked at we spent some time looking at the document that was put together by the Federal Highway Administration back in the year 2012. And I believe that's the second edition, or actually the 4th edition of the HEC or HEC 18 manual, which is a fundamental government-backed document on scour and how to work with scour. So, and the document is called Evaluating Scour at Bridges. It's a very comprehensive document. We were only able to take a bird's eye look at this document, but today we're going to be going in more detail into some of the portions of this document. Let's see, I have chapter 6, basic concepts and definition of scour. I already covered this, but I'm just covering it again because it's important. Scour can be deepest near the peak of a flood, but hardly visible as floodwaters recede and scour holes refill with sediment. So sometimes we wonder, the bridge failed, but it doesn't seem to be that there's a hole in there. So how come did it fail? Well, it failed during the rising limb, and then the hole filled during the receding limb. That's the way it happened. Scour can be of 2 types, clear water and live bed. And I think I already expressed to you a little bit of confusion as to exactly what these terms mean or what they are, but so be it. It's part of the document, the main document. So we're gonna have to go with what they say. So clear water scour occurs when bed material is not being transported upstream of the crossing. And live bed scour when bed material is being transported upstream of the crossing. So the clear water scour is mostly for cases of gravel and for flows that do not have a whole lot of speed or velocity. Total scour consists of 4 types of scour: possible degradation of the riverbed, long-term degradation, contraction scour at the bridge, because most bridges are built or designed including a contraction of the cross-section. Why is that? I don't know, but that's the way they do it. I think it's to save money, but that puts a wrinkle on the actual safety of the bridge, and bridges fail due to contraction scour. Local scour at the pier or abutments, because that's going to be a 3-dimensional flow in there of sediment, which of course we know nothing about, very little. 3-dimensional flow of water and sediment. And possible lateral migration of the riverbed. Also, that could happen. In many rivers that are very active, and they are meandering, they can meander and completely leave the premises and go somewhere else. So the bridge is left. The bridge could be correctly built from a load standpoint, but it's out of the river already. That has happened in many instances. Degradation is the scouring or lowering of the stream bed over relatively long reaches. Contraction scour, I already talked about that. Local scour, removal of material from around piers, etc. Clear water scour, contraction scour, we already covered that ground. Live bed scour and local scour. Okay, so I urge you to review this as you prepare for the exam. because this is just a summary of the main document. The factors, these are all the factors. And then an increase in flow depth can increase the scour depth by as much as a factor of 2 or greater for piers. Pier width has a direct influence on depth of scour. And that's the reason why the formulas that we're going to cover today and next time we meet have pier width as one of the factors. And these formulas, by the way, that are quite different. There's 3 formulas that we're going to cover. They are quite different from each other. They were developed from various people, mostly in academia or the government. They came about from different angles. And so we will see there's no rhyme or reason as to exactly how these equations were developed. What we know for sure is that they are empirical. They're empirical equations. They have odd numbers as coefficients and exponents. And that's the state of the art, I guess I could say. There is no such a thing as a numerical or phenomenological procedure to calculate a scour hole. We don't have such a thing at this point. Hopefully in the future we will. Once we develop a model of 3-dimensional flow of water, then the next step will be, maybe 5-10 years down the road, to develop a model of 3-dimensional flow of water and sediment. Okay, so let me just stop in there. I'm going to move on to the next document, which is something that I think you guys are going to be liking. Bridge failure, Kingman, Arizona. This is the only time in my entire career that I've dealt with specifically with a scour failure. And this is the failure of railroad bridge number 504.1S near Kingman, Arizona. And that's one picture. I actually have a collection of pictures, but you know what? I don't know exactly where they are. But this one's happened to be very handy. So I put it in here for you guys to see. It is also part of the main report. And it's also, yeah, that's right, part of the main report, because I am going to show you the main report. So this is the failure of Railroad Bridge 504.1S near Kingman, Arizona. This happened on August 9, 1997. And the way this thing worked out, if I remember correctly, is that there was a company in I was going to say Idaho, but it is not Idaho. It's somewhere out there, one of the states, Nebraska. There's a company in Nebraska that was hired to do the hydrologic study right after it, because it's always like that. Those are hindcast, by the way. You know, in design of engineering, there's forecast, and then there's hindcast, and there's actually design. Those are 3 different things, by the way. The forecasting is when you are forecasting that something's going to happen. That's a very difficult thing to do because you don't know when and how it's going to rain. The hindcast is what we're doing in here. Basically, the bridge already failed, and we're going in there and trying to figure it out a sort of post-mortem. Why is it that it failed, right? There's a hindcast. The design is just for design. The design does not consider that it's going to be a flood over there or anything. Just goes in there and says, what's the frequency according to established standards? And that's, we're going to size up the structure in one way or the other. The problem with these bridges, the main problem with these bridges is that they are old. They were put together something on the order of the turn of the 19th century. 19, right. So at this point, many of those bridges are about 120 years old. And they were built with wood, as you can see. They were made out of wood. And how many are there? There's hundreds of them. There's about a bridge every half a mile or something like this. And this goes for a couple 100 miles through all Arizona. So there's hundreds of these bridges. So the question is, you have hundreds of these bridges, they're old, they're going to fail. One of them is going to fail because there's going to be a big rain event in some watershed, some of those 300, 500, 400 watersheds. One of them is going to rain a lot, intense, very intense rainfall. And maybe those watersheds are not big, by the way, they're kind of small. But at any rate, this bridge failed. And it failed on August 9, 1997. And the gentleman that was hired to do the hydrologic study knew me from some other previous engagement that we have had. And so he called me up to back him up on whatever he was saying in the report. So I reviewed, I went over there, looked at, they took pictures and so forth. What happened here was that there was a derailment of the Burlington Northern, I believe, railroad. It derailed, as you can see. You can see the cars up here, the train car, sleeping car 32051. It's right there, okay? Why did it fail? It failed because there was an extreme hydrologic load in there, which I am going to qualify later on by saying it wasn't extreme. So there's something in here that, to be honest with you, I am not 100% sure. So I'm just going to show you the kind of the story, because the actual technique, exactly why it happened. I know for a fact that this thing happened because there was an erosion of the pile. How deep was the pile? I don't know exactly. I don't remember at this point, but I'm guessing that below the grading here, it probably was 4 or 5 feet, 6 feet high. I mean, deep in there, and it failed. And it failed because there was a hole in there, a scour hole during the event, which of course, after the event doesn't show up. Like I already told you, it fills up. There was also the failure of a wall that was in there. This concrete piece in here is a wall that my understanding is they were standing over here, and it failed also. So not only there was a lot of erosion on the sides and so forth. Erosion on the sides is interesting because we've been talking about erosion in the bottom for most of this class, but there's also erosion on the sides. And I'll have an example. Our next example, real life example, is one of erosion on the sides. The one that I mentioned to you that happened the year 2017 in Lima, Peru, of which I got the documentation. So let's move on in here. Now we're going to do something that we have not done before, which is to show you, if I can get there. No, I can't. Okay, where we go? Here we go. Okay, I'm going to show you the report, the actual report. Derailment of Amtrak Train 4, Southwest Chief on the Burlington Northern Santa Fe Railway near Kingman, Arizona on August 9, 1997. This was the official report. And the report was dated several years later, by the way. It takes the transportation, what is it? Transportation accidents or transportation safety. Let's take a look. Oh, the National Transportation Safety Board. Because I had been involved with this project, I was able to get this report, which by the way is dated. What's the date of this report? I don't know, it doesn't say. Some of the documents that the government puts together don't put dates in there. Let me see, 9803, I don't have a date in here, nor in here. So I can't tell you exactly what was the date. Obviously it happened afterwards, right? Probably a couple or 3 years later. My guess would be that it's even 4 or 5 years later, because everybody's got to be consulted, and this is the official report. It's about 100 pages long. So if you guys are interested in something that has to do with how these reports are put together, I mean, you're certainly welcome to take a look at this report. It's very comprehensive, exactly trying to figure out who was to blame, was it chance, was it poor design, and so on and so forth. So there's a lot of hydrology in this report, a lot of hydrology. And obviously, I'm not going to read the entire report for you because I'm going to leave it there for you if you're interested to read about it. I'm not going to quiz you on it. I'm just showing you the practice, the actual practice of hydrology and sedimentation engineering. This was notation August 1998. I was wrong there. I said 5 years. No, it was in August 31, 1998. And the failure was in August 1997. So it took him about a year to put this thing together. Results of Ares Associates. They're mentioning Ares Associates, by the way, as the main company. I am guessing that Ares Associates hired my friend in Nebraska to do the work because they were kind of doing it together. I never saw Ares Associates. I never communicated with them. I was communicating with the gentleman in Nebraska. But typically that happens, by the way. Sometimes 2 or 3 companies get into some job or some project, which is what was done over here. What did Ares Associate was asked to do? To reanalyze the hydrology and hydraulics and conduct a detailed scour analysis of the failure. determine the relationship between the scour and the ADOT reinforced concrete box culvert located approximately 1,000 feet downstream. So there was a claim that anytime you have a failure here on this site, there are situations, local situations that perhaps make it possible for two structures to have interacted with each other and so forth. That's why they're saying in here, determine the relationship between the scour at the bridge and the ADOT reinforced concrete box culvert located approximately 1,000 feet downstream of the creek. The creek, by the way, doesn't have any name. Why? It is, like I already told you, there's 1,000 creeks out there. They don't have names. Here is associate final report. Here, I'm going to change what I just said. I read this thing yesterday, but I don't remember everything. It says, final report, hydraulic erosion and scour analysis of 1997, March 2001. That's a final report. That means after that, ARIS was released from bondage, so to speak. But those reports go through 2 or 3 years of reviews by this agency, that agency, and so forth. So that's the last date, March 2001. The historical timeline is very interesting. Year 1883, that's when this whole thing started. Year 1907, bridge 504.1 north, replaced on driven timber piles. South track constructed on mud sills or on hard pan, 1922. So when this thing failed, it was about 100 years old. Let me repeat that. When this thing failed, it was about 100 years old. For how many years do we expect these bridges to go? Typically it's 50. So this thing was going to fail no matter what. So why didn't society or the owners, Burlington Northern, go in there and fix the thing when they were supposed to fix it maybe 50 years ago? Because if it ain't broke, don't fix. That happens everywhere. That happens everywhere. Now, in retrospect, now I believe they realize that if it happened once, it'll happen again, and it could happen anywhere. So they are actually reviewing and checking every one of those bridges to make sure that they're safe. That's a tough job. There's too many of them and so forth, and you really, really never know, because you're gonna have to get deep into the soil and so forth. That can't be done readily. It's extremely expensive. So what they could do is to replace everything, but that's also extremely expensive. So as you can see, it's a wait and see attitude in here. And I do believe, if I'm correct, that these bridges had not failed. This was the first one that failed. So it gives us the idea that if one failed, the others will, because there's, like I said, there's a ton of bridges out there of the same type. They're timber pile bridges. Why is that? Because that area of Arizona is so flat that there is no concentration of streams. So the streams are all over the place. It's flat, and so you never know when and how it's going to rain. In this case, it rained. Now, the question is, maybe we could say, or somebody could argue, well, this is going to happen, and most likely the 100-year flood hit this bridge, and it couldn't take it, and it failed. Well, no. The calculations have shown that the 5-year flood is the one that hit the bridge. And this report says that. It was not that big. So why did it fail? Perhaps it failed, it was just so old, not necessarily due to the heavy load. Because like I said, at the beginning, I thought they were going to be hit by 50 or 100 years, but that apparently has not been the case. It was not that large a flood that went through here. 19 square miles, nothing. Over in the flat terrain of Arizona is nothing. So there's hundreds of these very small basins. Hydraulic calculations, and so on and so forth. And all this is the history of what happened on that site. And I'm going to skip over this now. Very comprehensive. Flood frequency relationship for bridge 504.1S was determined. Range for plausible peak discharge value for the flood is 450 cubic feet per second to 875. So they even have a range in there. They can't really commit themselves to one value. Because like I said, hydrology is fuzzy. I remember I told the people our class in hydrology is fuzzy. 20, 30% is not inappropriate. And here we got almost 100%, from 450 to 875. They're saying they can't determine the discharge. It varies between 450 and 875. The peak flow of 875 is found to have a recurrence interval greater than 2 years, but less than 5 years. So it's not a huge flood, and yet the thing failed. And it failed, it kind of set on it, okay? Maybe it was also the failure of the wall that kind of sat the whole thing for a few centimeters or inches. And then when the railroad went through at night, it was like at 10 or 11 o'clock at night, it's dark anyway. The settlement of the railway was enough to derail the bridge, derail the train. And there's another thing in here that has come up on the report. They said that they should have better control on the speed of these trains, because the speed of the train is controlled by the guy that is in charge on top of the train, right? I don't know what they call it. The person that drives the train, okay? And that person is in charge of the speed, like anything else, okay? And if what I have read in this report is that perhaps, just perhaps, had he lowered the speed at the time that it rained and going through the storm, because it was a storm, they were going through a storm, that perhaps it would not have happened. It's just a perhaps, okay? But the point is that was one of the conditions or considerations that they had, perhaps controlling the speed. And what I believe that they have done is that lower the speed when it rains, which is the way it should be done, by the way. Everywhere. When it rains, you lower the speed to half of what it is. Otherwise, you can run into trouble. So that's some of the stories. As you can see, this is not just sedimentation engineering or hydrology. It's also usage, it's all kinds of stuff. It's luck also. Why is it luck? Because whenever there's a storm, the railroad sends an inspector 2 or 3 hours before. And they did that. They send it, they tell the story. They send the inspector 2 or 3 hours before, like at 8 o'clock at night, they'd send the inspector, and the inspector reported nothing strange. Go ahead, continue. There's nothing that's happening. 8 o'clock at night. And then at 11 o'clock at night, the train derailed in 504-1S. So that's luck. Why is luck? Because what happened was, obviously, from my experience, that at 8 o'clock, nothing had happened. But by 11, 3 hours later, something was happening at that bridge. It had settled. How much? A few inches, but enough to derail, because the train is not good with some change in the grade. If the change in the grade is minor change, it'll still derail, as it happened over here. Okay, so I'm going to proceed with this. As you can see, a very detailed report. They must have spent hundreds of thousands of dollars to pay Ares to produce this report. And hopefully they have recommendations, and then they learn from it. That's why they do it. They want to learn. They want to make sure that the incidence of these types of failures is reduced in the future. That's why they spend all this money, which is correct, by the way. Beginning of page 60 is revised as follows. As you can see, they revised the work of Ares Associates. Perhaps they didn't quite like the way they stated it, and so on and so forth. It's all in here. You can see. It's a good story about them, by the way. Good story. So we have the contents in here, executive summary. Let's read the summary, and then we'll just skip it. 5:56 a.m., 1997, derailed. So I was wrong. I said at night. It was in the morning. Derailed in the Burlington Northern. The train was traveling about 89 miles per hour when both the engineer and the assistant engineer saw a hump in the track. They applied the emergency brakes. The train derailed as it crossed the bridge. Subsequent investigation revealed that the ground under the bridge had been washed away by a flash flood. Exactly, that's the way it happened. Not uncommon when you have a flood and you have all these situations put together. Factual information, and so forth. There it is. Aerial view of the derailment looking south. You can see the creek over here. And I'm not sure at this point if the flow is going that way or this way. To be honest with you, I am not sure. I would guess that it's going this way. In other words, going toward us. But that's just a guess based on information. I was there, actually. I was physically there. But it's been 20, how many years? 25 years ago. So I don't remember everything I saw 25 years ago. But I can guess, since I was there, it's better to have been there than not to have been there. Where's the Kingman site? It's about an hour south of Vegas, or Las Vegas, in Arizona. Flagstaff, Seligman, Kingman, Phoenix. You know all that stuff already. So post-accident events, that's a picture of the actual site. Flow of water under the bridge. After the derailment, the water was still flowing a little bit, and so forth. Injuries, there were some people injured. Nobody killed, by 312 people injured on the accident. The train came to an abrupt stop, and it kind of lay on its side. So there were some injuries. I would not have liked to have been there. It's 300 total, 300 injuries. I'm sure they had to pay reparations and so forth. That's another story. Personnel, okay, here it is, damage to the side. So in summary, what happened here? Old bridge, built 100 years old. It was more than 100 years ago. It was repaired here and there, but not totally, completely repaired. And it failed. And it failed because of the piles were at a certain depth, and the erosion at that time, the local scour was large enough to undermine the foundation. And on top of that, there was a wall on the side, and that wall also failed because we see the wall on the floor of the creek. So that could not have helped at all to the situation. So at any rate, I'm going to stop in there. Oh, there it is, there it is. That's the design of the bridge out there. That's the bridge. That's the way they used to do it. This was 100 years ago. The bridges were made out of wood. I'm sure there are many out there still. Okay. This is the box culvert downstream. This is the downstream culvert that they are saying. They're saying that it may have interacted with the flow over at the train site. That box culvert is for a highway crossing. This is a highway out there right next to the bridge, by the way. Okay, so with that I am going to consider that we have reviewed this and explained to you. So now I'm going to move on to failure of Solidarity Bridge. I have two. I have an MP4 and a MOB. I'm going to go with the MOB because the MOB is more complete. I think it's more complete. So I'm going to go with failure of Puente Solidaridad. In Spanish, that means Solidarity Bridge. So let's take a look at the failure. Did the bridge fail 3 times? No, it failed only once. It fell down only once. It collapsed only once. I repeated the clip 3 times so that you could see it better. Okay, you could see it again and again. What happened there? Well, let's take another look. The abutment fell because the foundations of the abutment were eroded. Now, if I had been there, or if I had been there earlier, or if I had been in any way associated with design of the bridge, we probably would have asked the question, what happens if the size of the channel of that river, it's a very powerful river. It's a very large watershed. It goes exactly through the downtown Lima, Peru. Okay, it's a very important situation out there. So as you can see, the whole thing was unprotected. It was anybody's guess when it was going to fail. So I don't know. I can't tell you. I wasn't there. All I did was I was told about it, and I was able to retrieve the video from, there were several videos, by the way. I retrieved this video, which appeared to me that was the better one, from YouTube, and I was able to manipulate it to show you just the part that I want you to see, which is the actual failure. So as you can see, this kind of goes on to prove that we can do a very, very good calculation of the Einstein method, but the Einstein method only deals with vertical erosion. It doesn't deal with horizontal erosion. And this is strictly horizontal erosion, stream bank erosion, not stream bed erosion. And in stream bank erosion, we are at a start, very little. Common sense is very important in this regard. This particular bridge was interesting, and it caused a lot of furor and havoc, actually, because it was supposed to be a pedestrian bridge, but it was supposed to be suspended. So basically, that structure over there, the abutment, was there for the heck of it. It was not supposed to work. In other words, if the abutment fell, the bridge was supposed to stand because the bridge was suspended on the other side. But as you can see, what happened was that once the abutment failed, the bridge failed also. It fell down. So exactly why and how, I'm not privy to those details. I wasn't there and I have not pursued it. All I'm showing you is a situation where I repeat, that it is not enough to do an exact calculation of the vertical movement, because there's also bound to be some horizontal movement of the river. And the rivers do move horizontally all over the place, right? So we need to be respectful of how the bridge is going to move. Okay, so now that we finished with those pictures and stories on the case studies, we're gonna go on to this document F06, which is called Bridge Scour. It's an online article. This Bridge Scour is an online article that was put together by me about 3 or 4 years ago, particularly for teaching this class, okay? And the first thing I do is show the only experience, direct experience that I had, actually practical direct experience that I had with Bridge Scour, the one in Kingman. So let's take a look at what I said in here. Bridges are road structures designed to make it possible to cross a river. Bridges differ from culverts in their shape and in that they're usually much larger. Generally, bridges are justified in cases of road crossings with major rivers, or when the great volume of vehicular traffic requires it. In many cases, the abutments and or piers are placed directly on the bed of the streams or rivers, which forces the need for a stability analysis. The stability analysis of the bridge itself and the piers and abutments. Here is an example of a couple of piers on the Sado River. And this is in Portugal. I was in Portugal, I don't know exactly, but it was probably 10 years ago. No, I take that back. It was the year 2010. I had an engagement in Portugal. Somehow I was there for about a week. And one of my friends, former students out there in Lisbon, took me south. He wanted to show me a few things south. And then we ran into this bridge. So I took the opportunity to take a picture. This is the Alcácer do Sal in Portugal. And the river is the Sado River. Sado in Portuguese means salty, salty. It's a salty river. Exactly why, I don't know. But there are some rivers that are salty. That depends on where they go through and so on and so forth. That's another story. Another good picture that I have in here is the bridge over the Kings River near Stratford, California. This is about 4 hours from here. 2 hours to LA and then 2 hours to the Central Valley. This is in the Central Valley, the Kings River. The Kings River is one of the rivers that drains Tulare Lake. That's another story, very long and involved story. Tulare Lake sits on the extreme southern part of the Central Valley. Tulare Lake, T-U-L-A-R-E. I am not sure, I would venture to guess that you guys have not been there. I was there many times over the course of the last 10 years because we were studying salinity. And the issue of salinity is like a very good place. Tulare Lake is a very good place to study the ins and outs of salinity and salinity effects and so on, and everything that has to do with salinity. And the issue is very complex, and we're not here to talk about salinity. So I'm going to leave it aside, but I have, those of you that have taken environmental hydrology with me last year, would remember that I did speak about Tulare Lake and its salinity problems. So north of Tulare Lake is the Kings River. So this is the Kings River. And the Kings River is a tributary of the San Joaquin, which moves north and then eventually drops its water into San Francisco Bay. So stability analysis includes the study of scour of one or more piers of a bridge crossing. During the passage of a flood, the flow is forced to go under the bridge. Why is it forced? Because the bridge occupies space, and that space, the flow is not going to go through that space, obviously, right? So there's going to be acceleration of the flow as it goes through the bridge. And that's what causes the failures of the bridge. If the bridge were a bridge that doesn't have any columns, then it would be nice. And you have a bridge that doesn't have any columns. Sure, you can, but it's more expensive to design. And I'll show you an example later on in this same document. Okay. The presence of one or more abutments reduces the effective cross-section of the flow. Therefore, the velocities increase with this, the sediment discharge. We know that the velocities are related to the sediment discharge by power from 3 to 7, average 5. So if the velocity doubles on a relation that has an exponent of 5, the sediment transport is going to go 32 times because it's 2 to the 5, double to the 5. 2 times 2 times 2 times 2 times 2 is 32. So therefore 32 times. So as you can see, higher velocities always impose possibilities for failure on the bridges. This process eventually leads to the undermining of the soil around the pier, which is, if of sufficient magnitude, can endanger the stability and lead to the eventual failure of the bridge. Most bridges that fail out there fail through erosion, scour. I think that's been documented. There are some bridges out there that fail due to earthquakes. And we've had failures due to earthquakes. In the year 2010, there was an earthquake in Los Angeles, and there's a couple of 3 bridges that failed. That was a very strong earthquake. But that's not as many. Scour is more common. So we are still learning how to design scour. We have not completely learned. And there's always a risk, of course. There's hydrology and design is always a risk. You can impose a certain condition for design, but that could be superseded by some fluke, luck or something like that. Scour is a transient flow phenomenon which occurs during the passage of a flood. The process is dual, characterized by 1, erosion during the rise of the flood hydrograph, and 2, deposition during the recession. In many cases, the hole produced by the erosion during the ascent is filled by the deposition during the recession. The failure occurs when the depth of the hole, called the depth of scour, is of such magnitude that it compromises the lower level of the foundation. Therefore, the objective of the analysis is to determine the depth of scour that enables the design of the bridge foundation with an adequate safety factor. So in here, we use a safety factor. Well, of course, in hydrology, technically, there's no such safety factor. The safety factor is implicit in the frequency. So if you say, I don't like the 100-year flood, let me put the 500, and then we go to 500, then you already have a safety factor in there. That's not like structures. In structural design, the safety factor is directly on the load and on the material. So in structure, by the time you apply a factor of 3, a safety factor of 3 on the load, and then apply another factor of 3 on the material, then you end up with a factor of 9. And that's the reason why buildings normally don't fall out of the sky, right? I know there's failure of structures, but not that often. I mean, we have millions of structures around the world. Every once in a while, we have a structure failure, but it's not that often. Well, bridges is more often. The failure of bridges due to scour is technically more frequent than that of buildings. Okay, types of channel. We already covered this ground. General scour, contraction scour, local scour, and lateral migration. The lateral migration is something kind of interesting because it's really not supposed to happen. I shouldn't say that. It does happen, but we're kind of not prepared to handle it. Most engineers are looking at the bridge and trying to figure out, if the bridge can stand or not. In the case of lateral migration, the bridge is standing, but the river has gone elsewhere. So the project still failed, but it didn't fail due to an issue of scour, a local scour. It failed due to the fact that the river moved somewhere else. It meandered and moved. Does that happen? It happens all the time in many places. I've seen it with my own eyes, by the way. And I'll explain to you later on. General scour is caused by a reduction in the supply of sediments in sections loaded upstream. Generally, this is due to the degradation immediately downstream of a dam, caused by the phenomenon of hungry water. This is something that our Professor Lane contributed a whole lot in the year 1955 when he wrote that famous paper, or that I guess you could say that seminal. It was a seminal paper on the Lane relation, which we already have covered extensively in this class. There are cases where you have changes upstream in the watershed, and that causes either aggradation or degradation downstream because the stream is trying to seek a new equilibrium. The stream, Mother Nature is always trying to seek equilibrium. If you impose non-equilibrium, Mother Nature will try to seek equilibrium from there on. It may take a while, but it will try to impose a new equilibrium. And the new equilibrium is different than the old equilibrium by definition. So there's going to be changes in the bed. We don't like that. We rather have the bed not move at all and for a long term, but it does happen. And that's why this subject is covered in here, because designers will go out there and design for contraction, design for scour, and then forget about the fact that in certain situations, there also may be a general scour problem. That's why they are pointing that out. This is the famous picture that Lane put in his paper. You've seen this picture before. Degradation below Fort Sumner Dam, Pecos River, New Mexico, Lane, 1955. I do believe I have a link in here. So that goes directly to the paper by Lane. We also have another picture or another photo of a scour. And this is exactly not a scour, even though it looks like scour, but it isn't. What this is sand mining. Sand mining in this particular river, which is the Guadalupe Creek near Ensenada. It's about 10 miles north of Ensenada, Guadalupe Creek, on this valley over there. I don't remember the name right now. General degradation due to sand mining. So technically, the general degradation here is not caused by adjustments to the slope by nature, but rather by dredging, taking the sand out and mining it and taking it somewhere else for usage, for economic usage. So why is it that this particular river has been mined extensively, I would say? I think in here we're talking maybe in meters, maybe 3 or 4 meters were dug under this bridge to the point where they revealed the foundation of the bridge, of the pier. It's a good foundation, by the way. At the time, we did the study, by the way. I take that back, what I said earlier, that I had only one example or one experience. Actually, there were two. There was also this one. We did an extensive study in the year 2012 of everything that happened in this basin, Guadalupe River Basin, Guadalupe Creek. That was 2012. We did a very extensive, it took us 1 year to do this work, but that included everything, not just the bridge scour. And that's why I kind of forgot about it earlier. But we did extensively study this bridge, and I'm going to ask you to do a calculation with it because we got the data. So you can, run the data again and do the calculations with the various models that we have. I'm going to ask you to run HEC 18 if for any reason, because HEC 18 is the most common method. And then I'm also going to ask you to run the complete method put together by Professor, his name, I don't remember right now, but we'll get there. Okay, so we have it here. So we're going to do this calculation next week, and then I will have a homework for you. I think that's going to be the last homework of this class. So you will learn how to calculate depth of scour by two methods. And then I'll ask you to come up with an answer to what should be the design. Typically, the design includes a factor of safety, which is unusual. And it is unusual because typically the factor of safety in hydrology and hydraulics is built into the frequency, particularly in hydrology. So if you're talking about a factor of safety by adding a certain amount to the depth of scour, then that looks more like structural engineering, adding a certain amount, which is fine. That's the way we do it, because we want to always to have a certain factor of safety. That's the issue, factor of safety, very important subject in engineering. What was the factor of safety in the case of Hurricane Katrina? That's a very interesting concept. And that's soil. That was geotech, actually. It wasn't sedimentation. That's why I didn't include it in here. It was a geotech problem. The Army Corps went in there and built this wall on top of mud, on top of muck, actually. And they figured out that the factor of safety, or rather, what was it? At the end, when they went over there to examine what had actually happened and why had that wall of concrete tipped over and failed, and 2,000 people, I believe, or 1,000 people were killed that night. October, I think it was 2007, if my memory serves me right. They figured out, because of that, there's a report on it, by the way. It's a geotech report, by the way, so that's why I didn't include it in here. That the factor of safety was 1.3, and it had, during the failure, it had come down to 1, and then when the factor of safety comes down to 1, the thing tips over, right? That's exactly what happened. Why is it that the Army Corps was designing these structures with such little factor of safety? That's another issue that needs to be answered. It's a small factor of safety, 1.3. Admittedly, the geotechs use very low factors of safety. That is true. 1.5. 1.5 is typically geotech. Why they did 1.3 in here, I don't know. And on top of muck, I would not have done it. As a matter of fact, I would have never done that kind of story, that kind of situation, which is a vertical wall, because we know a vertical wall can tip, which does not happen in an embankment. An embankment cannot tip. The embankment can breach, and flow will go through the embankment, but in a slow fashion. It will take a couple of days for the whole thing to flood. In this case, it was violent. It didn't give any time for people to run. It's like an overflow of a glass of water. If you have a glass full of water and you put a blunt object inside the glass, what's going to happen? It's going to overflow immediately, right? We can tell you exactly why, but it is like that. It overflows immediately. Intuitively, it will overflow immediately because the speed of the wave on the surface is so fast that it is almost infinity. That's the theory, the fluid mechanics theory on it. Okay, continuing here, contraction scour usually manifests itself through the width of the river during the passage of an extraordinary flood. So this is the bridge over the Cuyabá River, Mato Grosso, during the flood of January 10. I've been in the field many, many times, and typically the floods follow me. If I go out there, then there's a flood out there. And I've shown you cases where I was photographed, or I photographed the river directly on the flood, and I was on top of it. Likewise in here. In 1995, I went to Brazil because we had a contract to do the environmental impact study of the Paraná waterway on the Pantanal. Those of you that have taken environmental hydrology with me last year have heard me talk about that subject, and I ran into a flood. This is a flood. That bridge is not supposed to be that low. As you can see, actually, the water is not supposed to be that high on the bridge. And yet the bridge is fine. It didn't fail. It was correctly designed and so forth. It was standing. You can see the buses over on top of it. But this is a flood. It was flood stage. It was such flood stage that I was able to take a picture, a famous picture that I had in many of my videos of an area there, a rural area, which has about a couple of feet or say 0.5 meters above ground of water. So flooding was already at least 0.5 meters, if not more. Local scour, yes, and our example of the Kingman Bridge, which I already talked about. And finally, lateral migration. Lateral migration occurs when a river carries excessive amounts of sediment in relatively flat geomorphological situations, which forces it to fill its channel and consequently to look for new courses, usually during the passage of its extraordinary flood. In general, any widening or lateral displacement of a fluvial channel endangers the operability of a bridge placed on it, of course. You put a bridge and the river can move somewhere else, and then the bridge is there standing, but it's not operable, right? There doesn't seem to be a simple solution to this bridge design problem. There is no simple solution. And I give you an example of it here. What is this? This is the Kosi River, which, by the way, we worked on back in the year 1973, the end of 1993. No, excuse me, 1993. 1973, I was in Peru. No, 1993, I was in India. I got a hold of this document that described the Kosi River because our team went out there to look at the Kosi River to learn something about the Kosi River. It's a famous river. It's a famous river from the standpoint of sedimentation. So what's the actual geomorphology out there, actual location, the history of this whole thing? Well, what you see in here is the Himalayas. It's the base of the Himalayas. And from here south, that is the Ganga River or Ganges River, one of the largest rivers in India. And this over here is the Ganges River, over here. The picture doesn't show it completely. Where did the Ganges River come from? It comes from over here. So in India is big, right? So this is the Ganges River over here, the sacred river of the Hindu religion. And there's another river over here, which is coming from here in the corner. This is the Kosi, actually. This is the Kosi River. Okay, and it looks small, but it's comparatively speaking, with the Ganges, it is small. But as you can see this, the picture shows, for the last couple hundred years of record, this Kosi River has been moving around, and it continues to move around. Okay, why? Because it carries a lot of sediment, and all of a sudden it gets over here and it flatly hits the ground. Like this from here on is the Himalayas. The Himalayas go all the way up to 8,800 meters, which is about 20,000 feet of elevation. I don't know exactly what the elevation over here is, but it's not that high. So that means there's a lot of sediment being transported from the Himalayas over here. And once this sediment gets in here, it kind of gets carried over here, right? And supposedly it's going all the way to the river here in the Ganges River. But it cannot do that because it doesn't have the force. So what it does is it starts settling. And that produces the movement, the lateral movement. So this is technically not a meander. It is a lateral migration because of the geomorphological peculiar or particular situation of this river. First, it has a lot of sediment. Second, it's running on a flat land. So the sediment has nothing to do but to settle. So it creates these lateral movements, as you can see. That is an image, satellite image. But in here, we have a vector. So in here, that's the raster, that's an image. And in here, we have a vector that shows the data. And of course, I would not have been able to get all this data if I had not taken a look at the book that describes the situation. So I pulled together, and I believe I did redraw this graph over here. So this is the Kosi River, 1938 to 1940. But this is interesting. Let's take a look at this, 1938 to 1940. And mind you, the Kosi River is still there. It's still there. So this is the year 2022. So that means that for the last 100 years, the Kosi River has not moved? And the answer is yes. Why didn't it move? Because the government wouldn't let the river move. Just like the Mississippi. Just like the Mississippi. The Mississippi has been levied for a couple hundred years. The Kosi River was levied, started in the year 1935 or 38. Because prior to that, the Kosi felt free to move. And it did move. It did move. 33, 26, 22, 93, 1893, 1807, pre-1736. This is India, so they got data going back a couple, 300 years, right? Because there's settlement for a long time out there. So I have no reason to believe that this data is wrong. It is the data that they have. And the river Kosi did move for the last couple hundred years until the year 1938. The last time it moved, now it's there, because it has been forced to move. That's the kind of the story as is. But there's a sad story behind it, which I'm similar to the Mississippi, by the way. Because every time we deal with sediment, we gotta cite Machiavelli. If you win, you lose. You're never gonna completely win the fight against the sediment, because sediment is natural. And we are trying to accelerate things, always change things, not considering the long-term prospects. Okay, so in here what happened is that by the time they decided that they were gonna set the course of the Cosi over here, then they had to build a levee, because they don't want the river to go and encroach on the levees, right? So then the levees, they started with levees, and my guess would be that in meters, they would have started with 1 meter. But by the time I was there in the year 1993, the levees were 10-meter high. Similar to the Mississippi, by the way. Only that the Mississippi is, I believe, 1,500 miles. In kilometers, it would be 2,500 kilometers. Here, I don't believe there's 2,500, maybe a couple hundred kilometers at the most. I don't know exactly, but I'm gonna say that it's not more than that. So it's a shorter reach, but it has the same problem. Actually, a worse problem, because in here, you're getting the sediment directly over here, and trying to distribute the sediment is a tough problem. The Mississippi, no, the Mississippi is getting the sediment from the entire United States, Midwest, mid-central United States, and also a couple of provinces in Canada. We know that for a fact, but not here. So the problem that they're currently having is that even when the river floods, it wants to move, and it encroaches and fights against the levees. The job of the government over in India is to not allow the river to move. And they're doing that constantly. They have people all over the place out there working to make sure that the river does not move. But that, you guys know that that's counterproductive, because eventually the river will move. It may be 10 years, it may be 100 years, but it will move. It will breach on those 10 meters. The worst part of the whole story is that when it reaches 10 meters, there will be a lot of people killed, because 10 meters of flood, that's a lot of water, right? So I'm telling you something that has not happened, but in the future, the cards are there, it will happen. In retrospect, they should not have done it, in my opinion. But who is Professor Ponce to tell those guys 100 years ago that they shouldn't do that? After all, the Army Corps of Engineers had already done it in the US. And we, right or wrong, always serve as example to other people around the world that feel that we are better, or somebody or some institution or country to reflect or to copy. Okay, so I am totally convinced, because this has happened before, that since the Army Corps had already established the policy of building by levees, the Indian people went ahead and did it also. And they're now having to contend with the fact the situation out there is worse than in the Mississippi. Mississippi is kind of mild, slow, but out there is worse. So I don't have the current story on the Cosi, but it is a problem that continues. It is a major problem. What about this guy over here? Abandoned railroad bridge over the Piraí River, Santa Cruz, Bolivia. In 1989, I did a job, a 2-month, actually it was a 3-month job in Santa Cruz, Bolivia. 2 months and then 1 more month later on. We were charged with doing the sediment routing all the sediment on the Piraí, which is a Piraí basin out there in Santa Cruz, Bolivia. It's a major town out there. It's number 2 or number 3 town in Bolivia. Town? No, city. There's probably 5 million people in Santa Cruz at this point. At the time I was there, maybe it's 2 million, but it's grown out tremendously in the last 20, 30 years. But there's an abandoned railroad bridge over the Piraí River. And I was there and I took this picture to kind of prove on that the Piraí was a very unstable river. It was not leveed, so it could move around. And I do not believe anybody in the right mind would try to levee the Piraí, because it carries so much sediment that eventually it will do something bad. So now let's move into the contraction scour. Contraction scour occurs when the flow area is reduced either by a natural contraction or by artificial contraction due to the presence of a bridge. In most cases, contraction scour results in the deepening of the riverbed. Deeper channel will always have a greater velocity. And here we show the extreme case of the contraction scour, which I, from my own experience also. Figure 9 shows the Pongo de Manseriche. I do believe I have shown this, but it merits, and since only 3 minutes, I'm going to show it again today. It's a natural contraction sculpted in rock through which the Marañón River one of the two great rivers that eventually formed the Amazon, reduces its width to 35 meters as it descends the eastern Andes ranges in Amazonas, Peru. 35 meters. This is a huge river, one of the two tributaries of the Amazon River, further downstream. So there's a whole lot of flow out here. So if this is only 35-meter wide river, it must be very deep. So how deep is it? My understanding, and I'm not exactly 100% sure on it, but my understanding is that the aspect ratio here is from 1 to 100. So in other words, the depth is 100 times the width. I could be wrong on that, don't get me wrong. But it's extremely deep, extremely deep. One would have to just check it out on the web, I guess. I should have done it early, but I forgot to do that. But it's extremely deep. So this area over here that you see in there is what, 30 meter wide and about 2,000 meter or whatever it is, 2,000, yeah, I would say, stay at 1,000, it's already very, very large. The cross section, this must be, in all probability, the deepest aspect ratio of any river, anywhere. I have not heard anything like this anywhere. It's the deepest aspect ratio. Typically, the aspect ratio of a river is 10 wide, at least 10 wide for 1 deep. This one is the opposite. It's 1 wide and 20, 30, 40 deep, okay? So that's the video Ponce de Manzarriche. And we have a video, we have a picture and a video. We took this picture out of the video, of the central part of the video. How did I get this video? Well, I had worked in Ecuador for many years. I believe for about 7 or 8 years. And off and on, go and do some projects and so on. In one of those projects, I ran into a student of mine. He is a student of mine. He got his degree in Spain. And I was supervising him while he did his PhD in Spain in the year 2010, I believe. So he introduced me to this gentleman, Carlos Correa Loyola, who had actually transversed the Pongo in the year 2005. So let's take a quick look in here. This is a very dangerous situation due to the fact that the vortices and all sorts of dangerous stuff. People have drowned in this reach. Why these gentlemen that are my friends didn't drown? Because they were lucky and they knew who to hire. Because if you hire the right person, they'll do it. If you hire the wrong person, they'll capsize the boat and then you can be killed. The latter part is my captioning, or rather take from Google Earth, by the way. I flew Google Earth and I did that latter part. Look at that huge rock in the middle of the river. Not very exciting. Darwin Palacios and Carlos Correa Loyola, he's the guy that gave me the video, from Loja, Ecuador, navigated the Pongo de Manzeriche in November of the year 2006. They're the two gentlemen. Okay, so now we move on to, no, we're here now. Okay, so now we are going to go into, let me see, the title or the topic is contraction scour. And I showed the contraction in here. The most contraction, by the way, natural contraction, and the scour created by the contraction. Mind you, this scour is on rock. So how many years did this take to form? My guess is in the 4 or 5 million years, maybe longer than that, millions of years, because this is not sand, this is rock. The Marañón River had to breach through rock in order to get to the jungle on the other side. And that's the way Mother Nature decided to do it. That's called a pongo. There's 2 pongos in this area in Peru, meaning breaches through the rock. And the pongo is a local name. It's an Indian Quechua Quechua name. Comes from, its origin is in the local language. So it's called pongo. That's why it's not, the word is not known in English. Okay. Here we again referred back to the issue of under clear water, under a live bed. I think we already covered the ground extensively, even though it's not 100% clear exactly what our friends from HWA, Federal Highway Administration, exactly what they are meaning when they say that. But there are formulas. There's a formula for live scour under clear water, and another formula for live scour. And that's what we're going to look at, the formulas, hopefully today or the next time we meet. Again, here, live bed scouring occurs for higher fluid numbers, for which the average velocity is greater than the critical velocity necessary for the start of bed movement. Everybody knows that there's a critical velocity necessary for the start of bed movement. But so then the question is, what's the flow right there? Is it less than the critical velocity, or if it's more? If it's less than the critical velocity, it'll have a tendency to deposit. We know that for a fact. We studied that already. And if it's more than the critical velocity, it'll have a tendency to move it. Okay? In this case, the flow area in the section of the bridge increases until the amount of transported material leaving the control volume is equal to that which is entering. So they are actually trying to do a balance in here. Existing formulas for contraction scour require the determination of the type of scour. To determine if the flow immediately upstream of the bridge is producing bed movement, it is necessary to calculate the critical velocity. These are standard situations in sedimentation engineering. The following formula may be used. And this is kind of an empirical formula. Why is it empirical? Because the case of U is empirical. As you can see over here, the V sub C critical velocity, Y is the depth, D50 the diameter, and Q sub U is the empirical constant, which is equal to 6.19 in the metric system and 11.17 in the US customary system. So it's totally empirical. Where exactly did they get this equation? I don't know, to be honest with you. I haven't researched this particular area. I try to stay away from empirical formulas myself. You know, the work, most of the work that we've done has been either numerical or, which is not empirical. Numerical is by using numerical analysis to solve the fundamental complete equations of motion. So it's not empirical formulas. But these empirical formulas abound and occur in scour calculations. So the design geometry, analysis, and I'm going to go over here. I'm going to finish in this section, and then we can start next week with the calculations. In fact, to go to the calculations of the 4 methods that we're going to cover. Analysis of contraction scour depends on the particular geometrical conditions. The following conditions or the following cases may arise. Flow in the floodplain, the distance between the abutments is lesser than the width, equal to the width, or greater than the width of the main channel. And here, lesser than the width. This is kind of bad, but it's done, by the way. The abutments, as you can see, this is a channel. The abutments go into the channel. I would never do that. But I mean, you know, I don't design all the bridges. Or you can go like this, which is okay, it's better. The channel, the abutments are outside. Okay, this is still bad. Why? Because the flow that is going through here now is forced to go through the center of the channel. So you're still running under a flood condition, you're still running more flow through this section than you would otherwise. Or you can go like this a little bit. You can see here, it's a little more open, I guess you could say, for safety also. The velocities are going to be reduced and so forth. All this stuff, by the way, all this hydraulic can and should be calculated by Hegras, by the way. Hegras will do this very nicely for you. Steady or unsteady. And I think in hydrology, we already said that it's probably better to do just the steady, because you're doing this with design condition. So steady should suffice. If you were doing this for forecasting, that steady would not suffice, because you have to go second by second or from time to time examining what's actually happening. But design condition is just a bird's eye view of what's actually going to happen. So it's probably sufficient to use steady flow for a design condition. Because as you know, Hegras has both steady and unsteady. So you're given the choice, and you as a designer has to choose which one to use. We have covered this ground in our class, in the surface water hydrology class. As a matter of fact, we did that just yesterday. So those of you that are taking surface water hydrology, and I believe all of you, I think one exception, are taking that class. So you already know what I have said. Without flow in the floodplain, the section of the stream is naturally narrower in the bridge and the section immediately downstream, or artificially narrower on the bridge due to obstruction caused by piers and or abutments. There's always obstructions like this one, contraction scour, because we have a bridge, a pier in the middle. Why do we do that? We do it because the designers come in there and they do it. Typically, many years ago, like maybe 50 years ago, there were structural engineers that would come and design the bridge and put the foundations. They would hire the foundation guys to tell them what should be the depth of the foundation, but they would not involve hydraulic engineers. That was 50 years ago, or prior to 50 years ago. Then it was at about that time that, that the problem was presented, that the problem was that the design of the bridge had to be done by structural engineers, geotech engineers, and hydraulic engineers, because the geotech engineers don't handle the scour. And certainly the structural engineers don't handle the scour either. So since the scour was a major problem, somebody that was knowledgeable on the subject of scour had to come in as part of the design team. Unfortunately, the issue of scour is something that has only been developing for the last 40, 50 years. We didn't know anything before that. I already told you that Einstein, 1950. But even Einstein wasn't really talking about scour. He was talking about bed movement. Scour is more complex than that. I already mentioned that. So the modified Larsen equation is, I already exceeded my time, so I'm going to stop in here very conveniently. We're going to start in here when I come back next Tuesday on 3.2. And then we will cover 3.2, all this detail, 3.3, local scour, 4, all this stuff we're going to cover next Tuesday. Oh, we have a lot of material in there. And then at the end, we're going to do, I already told you this, unconventional stream crossings. Let me advance here what I'm going to say. There's a bridge out there in Monterrey, Mexico, that is suspended on one side, and it doesn't need the abutment on the other side. So basically, this is similar to the bridge in Peru, only the bridge in Peru did fail. This one has not failed yet, has not been tested for failure, but there's every indication that it will not fail. It is totally suspended in the air on one side. When I was there, I inquired, how is it that they decided to build this bridge? And they told me, one of the guys responsible said, well, you know, this bridge costs 2.5 times the normal price that we would pay for a conventional bridge. But we liked the design, we wanted to do it, we had the money. So they did it. They came out with this bridge over the Santa Catarina River. The Santa Catarina River is a mean river because normally it doesn't have any water. But when it charges tremendously. It can overflow its banks. Every 20 years, I think the Santa Catarina overflows its banks. You can see that's a huge river. And I have a picture that I believe I've shown you before, either to you or to the other class, where the Santa Catarina River in Monterrey, Mexico, is actually overflowing. So that's a huge discharge. We have calculated at the time, we did some calculations, 6,000 cubic meters per second. That's a lot. It's a lot. Compare that to the mean flow of the Amazon. The mean flow of the Amazon is 200,000 cubic meters per second. So 6,000 is already large because you know the Amazon has a width at Obidos of 2 kilometers. The width of the Amazon is 2 kilometers. And that's the narrow portion, not the wide portion. The wide portion you cannot see in the horizon. It's 50 to 100 kilometers wide. So it's a huge discharge. So for this to be 6,000 out of 200, it's a lot. I'm going to stop there and wish you a happy holiday, Thanksgiving with your family. And I'm going to do the same. My kids I have 2 children, one man and a woman, and married and so forth. So they're all here already. So like I said, wish you good luck with the holiday and all great things happening. And I'm going to come back to you next Tuesday. So at this point, I am going to finish the class. Thank you for your attention.